Alright guys, so in this last section of Unit 3, we're going to talk about how you can use your graphing calculator to calculate areas and percentages under the normal curve without having to use the empirical rule. We found out in the most recent section that the empirical rule is very convenient, very nice. However, it has to fall on a standard deviation in order for it to be applicable. And so the problem is when you want something that's not on a standard deviation, then the empirical rule isn't very helpful. Fortunately, though, the graphing calculator can actually calculate those percentages for us. So we'll talk about that in just a moment. Let's first discuss what's called the standard normal distribution. Now, we saw lots of normal distributions in section 3.2. Here in section 3.3, we're going to talk about a special type of normal distribution called the standard normal distribution. And what makes it different is that it's set up very nicely for us. It's got a mean of 0 and a standard deviation of 1. So I've got a picture there to illustrate what that looks like. Notice that it looks just like any other normal curve, but has some very nice values for standard deviations both above and below the mean of 0. Now, throughout our notes today, we're going to be using two different calculator commands. The first is called normalcdf. The second is called invNorm. So the first one, normalcdf, is what we're going to use to find the areas or proportions under the normal curve. So this is what we'll use in place of the empirical rule when we want to know when something is the area for something when it's not on a standard deviation. Now, the calculator command for those that will not have a menu is you'll start by typing in the lower bound, followed by the upper bound, followed by your mean and standard deviation. Now, it's only necessary to type in the mean and standard deviation if there's something other than 0 and 1. So if you're working on a standard normal distribution, you can leave those last two parts off. invNorm is actually a way of going the other direction. So let's say we knew the area or the proportion under the normal curve and wanted to know how many standard deviations above or below the mean. In other words, what the z-score for those values would be. So when we type that in, it'll look a little different. We're going to start by typing in the area to the left of our value, so the area to the left, followed by the mean and standard deviation. Again, if those are 0 and 1, you won't have to type those in. So let's take a look at some examples here. Let's find the proportion of observations from the standard normal distribution that are less than 0.54 for part A. So if we think about what that would look like, let's just draw a simple picture. You've got your standard normal distribution. Remember, in our standard normal distribution, the mean is at 0, and we want to know less than 0.54. So let's say 0.54 would have to be somewhere to the right of the mean. And so we're wanting to know what is this area that I've shaded in blue right here. Well, to find that area, we can't use the empirical rule because unfortunately 0.54 is not a full standard deviation from the mean. So instead, we're going to use normalcdf. So we'll do normalcdf. For the lower, we actually weren't told what the lower bound should be. When that happens on a standard normal curve, usually -10 is small enough to be considered too small for anything else. So the lower we'll use is -10. The upper bound, so the furthest we can go, is that 0.54 that we're looking for. And what's going to be kind of nice, at least for this first example, is that we're using the standard normal distribution, which means the mean is 0 and standard deviation is 1. So we shouldn't need to put the 0 and 1 after it. So to get normalcdf, here's the way you will get there. You'll hit the second button, followed by the vars button, where it says distribution over the top of it. So underneath the arrow keys, second, and then vars. And then option number 2 is normalcdf. You can see invNorm is option number 3, so we'll get to that option using the same way. Now, mine does in fact have a menu, so I'll go ahead and fill in for my lower, -10 should be small enough. For upper, 0.54. And notice for the mean and standard deviation, it already has those as 0 and 1. So I'm not going to change anything there. I'm just going to press paste. If you didn't have a menu, again, what I wrote down here, -10, 0.54, is all you should have to write down. And it tells us that the proportion of observations is about 70 0.5%. I'll usually go out to 4 decimal places when I write down these percentages. So 70.54% would be less than 0.54. Let's go ahead and do another example. So in the next example, we want to know what percentage of observations are greater than negative 1.12. So again, we've got our normal distribution. The mean is 0. This time we're at negative 1.12. And we want to know what the percentage of observations that are greater than that would be. So greater than would be everything to the right. So this time, when we go ahead and put this into normal CDF, our lower is now going to be the negative 1.12. Our upper, we don't really have. So again, going out to positive 10 should be plenty far enough. And since it's the normal distribution, the standard normal distribution, we shouldn't have to put the 0 and 1. So again, second vars, option number 2 for normal CDF. Our lower is going to be negative 1.12 this time. The upper is going to be positive 10. Again, mean and standard deviation, we will leave the same as 0 and 1 if you have to. If not, you don't need to type those in. And it looks like that's going to be 0.8686. All right, let's do a couple more. So for the next one, we want to know what percentage of the observations are greater than 3.89. So we've got our mean at 0. 3.89 is going to be way over here to the right. So it should be a pretty small number because there's not a whole lot of space out here for it to be. So again, we're going to use normal CDF. Our lowest bound in this case is 3.89. The upper bound, again, we'll just use 10 since that's going to be furthest past anything else. And we'll go ahead and get that typed in. So again, second vars, we'll choose normal CDF. Our lower this time is 3.89. Upper we'll leave as 10. Mean and standard deviation we'll leave there as well. And so that's going to be a very small number. Just a reminder with how this notation works, 5.01 e negative 5 tells you to move the decimal place 5 points to the left. And so when you write this as a decimal, you're actually going to end up putting 4 zeros in front of the 5. So 0.00005, and then we'll go out 0, 1. So a number very, very, very close to 0. And again, if you think about it, there's very little space out there to the right of 3.89. So yeah, you should have expected a pretty small number. Let's do one more. So for this next one, again, we're on our normal distribution. We've got our mean at 0. And we want to know what percentage is between 0.49 and 1.82. And we want to know what is this area in between those two values. So this time we actually know both a lower and an upper bound that we're going to have to type in. The lowest bound is the 0.49. The upper bound is the 1.82. Again, if you have to type mean and standard deviation, you can leave those as 0 and 1 or leave them off if you don't have to. So again, second vars to the distributions menu, we'll choose normal CDF. This time we'll have to type in both a lower and an upper, so lower is 0.49, upper is 1.82. Again, mean and standard deviation leave the same. And it looks like the area in between those two values is 0.2777 to the nearest fourth decimal place. Okay. So actually one last one, let's talk about within 1.5 standard deviations of the mean. So if you were to draw that out, you've got your mean at 0, and within 1.5 means going down by 1.5, so negative 1.5, also going up by 1.5, so positive 1.5, and we want to know what is this area in between. So once again, we're given both a lower and an upper bound. Our lower bound is going to be the negative 1.5. Upper bound is going to be the positive 1.5. So again, second vars, option 2 for normal CDF. We're going to go from negative 1.5 up to positive 1.5. And again, leave mean and standard deviation 0 and 1. And we should end up with 0.8664. So about 86.64% of the data is within 1.5 standard deviations of the mean. Which should kind of make sense because within 1 standard deviation is 68, within 2 is 95.7, so you would expect for 1.5 to be somewhere between 68 and 95.7. Okay, so let's take a look at how we're going to use inverse norm with this next example. So a distribution of test scores is approximately normal, and Joe scores in the 85th percentile. How many standard deviations above the mean did he score? Again, I would suggest drawing a picture. So we've got our normal distribution. We know that Joe scored in the 85th percentile. So what that means is that he did better than 85% of the other people that took the test, meaning that he's above 85%. So we know the area under the curve up until where Joe scored is 85%. And we want to know what is the z-score, or what is the number of standard deviations below that you would be compared to the mean. And so when that's the case, what we're going to use instead of normal CDF, because normal CDF would have given us the 85%, is we're instead going to use inverse norm. Now, for inverse norm, we're going to start by typing in the area to the left of that z-score, which fortunately for us is the 0.85 that we already knew. As for mean and standard deviation, it said that it was on the standard normal curve, so we shouldn't have to type those in. If we do, we'll leave them as 0 and 1. So inverse norm, same menu, second vars to get there. We're instead going to choose option 3 this time for inverse norm. For the area, we're going to use 0.85, which was the percentile we were given. Again, if you have to leave mean and standard deviation in there, 0 and 1. Otherwise, just close your parentheses and hit enter. And then we would know that his z-score is equal to 1.036. So how many standard deviations above the mean did he score? There's our answer. He was a little over 1 standard deviation above the mean. Now, in a normal distribution, Q1 is how many standard deviations below the mean. Well, let's set this one up kind of in the same way. So we'll draw our normal distribution. Our mean is at 0, but Q1, let's think about what that would be as a percentile. Remember, that would be the 25th percentile. So that would be an area of 0.25. So 0.25 would have to be somewhere over here. Again, the area for that is 0.25, and we want to know what would be the standard deviations. In other words, what would be the z-score would be another way to think about that. So when it says how many standard deviations, what it wants to know is what is the z-score. So once again, just like in the previous part of this example, we're going to end up using inverse norm. For the area to the left, we know that that area is 0.25, and if you have to leave mean and standard deviation in there, just leave those as 0 and 1. All right, so we'll change 0.85 to 0.25. Oops, 0.25. Everything else will stay the same. And that's going to be negative 0.6745. So a little bit less than 1 standard deviation below the mean. All right, let's take a look at some real-world examples of where we can use this sort of procedure. So in the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speeds is normal with a mean of 115 miles per hour and a standard deviation of 6 miles per hour. So this is going to be our mean, which the calculator will use mu for that, and then 6 is going to be our standard deviation, and the calculator will again use sigma for that. So this time we will have to put those in. Let's first just go ahead and draw out for part A a picture of what this is going to look like. So about what proportion of his first serves would you expect to be slower than 103 miles per hour? So remember, when you're drawing this one, instead of the mean being 0, the mean this time is 115 miles per hour. And then 103 then would be below that. So that would be somewhere over here. We want to know what proportion would be slower than that. So what proportion would be less than. Okay, so we want to know what the area is. And when that's the case, we're going to use normal CDF. For our lower, we need to pick something much, much lower than 103. I'm just going to use 0. Should be plenty low enough. And then 103 as the upper bound. Now again, because the mean and standard deviation are not 0 and 1, we will have to include those this time. So the mean is 115. Standard deviation is 6. So when I go into that menu for normal CDF, for the lower we'll use 0, upper we'll use 103, and then for mean we will need to change that to be 115 instead of 0. For standard deviation we'll have to change that to be 6. And for those that don't have a menu, here's what that should look like when you are done typing that in. So 0, 103, 115, 6. And then when we run that, we'll get our proportion. So we would expect for about 0.0228, so about 2% of his serves to be slower than 103 miles per hour. All right, let's do another example. So for B, so we've got our mean once again at 115. We want to know what proportion would exceed 120. So 120 is somewhere over here to the right of the mean. We want to know what proportion will be more than that. So when we set up our normal CDF, we're going to have our lower is 120. For upper, we need to pick something a lot bigger than 120. So we need to pick maybe like 200. Should be plenty big enough. And then for the mean and standard deviation, again, we'll leave those as 115 and 6. So back into our normal CDF menu. For lower, we'll change that to be 120. For upper, 200. And for mean and standard deviation, just leave those the same. And so it looks like about 20%, so 0.2023 would be more than 120 miles per hour. All right, so then for part C, what percent would be between 100 and 110? With the between ones, you usually are going to be okay to not have to draw out the picture. You can just use those for your lower and upper bounds. The picture is usually helpful if you're missing one of the two. But for this one, we're going to go from 100 to 110. Again, mean of 115 and standard deviation of 6. So let's go back in, choose normal CDF. Lower is 100, upper is 110. Mean and standard deviation will leave the same. So it looks like a little bit less than 20%, so 0.1961, so 19.61% of his serves would be between 100 and 110. All right. Now this last part is going to be a little bit different. So it says the fastest 30% of his serves will go at least what speed. So now we know what the percentage is, but we don't know what the actual value is. So when we're looking at this curve, and again centered at 115, the fastest 30% would be an area over here. So we've got this area of 30% that's the fastest. And we really want to know what is this z-score, or really not even z-score, but what is the value there. So rather than using z, I'll just use x. So we want to know what number would leave us with 30% above. Now here's the problem, is for inverse norm to work, you need the area to the left, not the area to the right. And the area to the right is 30%, but remember the normal curve has to add up to be 100%. So if the area to the right is 30, then the area to the left, everything over here, would have to be the remaining 70. So we're going to actually end up using 70% as our area to the left. And then we're going to also include our mean and standard deviation. That was something we didn't do last time, but now that we have those, we'll go ahead and include them. So second vars to get there, inverse norm is option 3. For area to the left, again, we'll type in 0.7. And then for our mean, we'll change that to be 115. Standard deviation will change to be 6. So if you're typing this out with the parentheses, here's what that should look like. And so then it looks like our value for x is going to be equal to 118.15, and those were in terms of miles per hour. So anything more than 118 miles per hour would be about 30% of his serves. All right. So for part E, a different player has a standard deviation of 8 miles per hour on his first serves, and 20% of his serves go less than 100 miles per hour. If the distribution of his serve speeds is normal, what is the average first serve speed? So a lot going on here. Let's just draw a picture to get a better idea of kind of what we need to do. So we don't know what the mean is. That's going to be kind of what we're solving for. But what we do know is that his 20% of his serves go less than 100. So somewhere over here, we have 100, and we know that 20% go less than that, so the area over here is 0.20. We also know that the standard deviation is going to be 8. But what would be really nice to know is at least what the z-score is for 100. So let's find that first. If we take inverse norm of the area to the left, which is 0.2, and since we don't know the mean just yet, let's just use 0 and 1 for a standard normal distribution. So we'll go into our menu, choose inverse norm, 0.2 is our area to the left. For the mean, we're just going to assume 0 for right now, and standard deviation of 1. So what that's at least going to tell us is that z is equal to negative 0.8416. Now, you might not see why that's helpful just yet, but let's remember what the formula for a z-score is that you take your value for the observation minus the mean divided by your standard deviation, which, let's plug in everything we know into that equation. So we know that z was negative 0.8416. We know that x was our value that we used before, so that was 100. We still don't know our mean, but we do know our standard deviation is 8. So we'll take that and divide by 8. So to solve for our mean, now we just have to solve this equation. So let's go ahead and start by multiplying by 8 on each side. So we'll take that number that we just got and multiply by 8. Is negative 6.732 or 733. We'll go ahead and go that far. Is equal to the 8 are going to cancel out, so 100 minus mu. So now we want to get our mean, which is mu by itself. So we'll go ahead and just subtract 100 from each side. Notice that I'm leaving all of this in the calculator so that it's an exact answer. So minus 100 is negative 106.73. I'll just go to the nearest hundredths place. Is equal to our negative mean. And if we want our positive mean, just make each side positive. So it looks like that this player had an average of about 106 miles per hour on their serves. All right, guys. At this point, I'm going to go ahead. I've got one more example that we can work through. If everything has made sense so far, you would probably be okay skipping this next example. If you want to go through a little bit of extra practice, though, it would be a nice example to work through to make sure everything makes sense. But again, it's really just going to be a repeat of a lot of the stuff we saw just now on that most recent example. So it's up to you to decide, do you want to see an extra example or not? I'm going to work through it either way. So suppose that Clayton Kershaw, who's a member of the Los Angeles Dodgers, throws his fastball with a mean velocity of 94 and a standard deviation of 2, and that the distribution of his fastballs can be modeled by a normal distribution. For part A, what proportion of his fastballs will travel at least 100 miles per hour? So let's go ahead and draw in our normal distribution. It said that the mean for our distribution was 94. And we want to know which ones will travel at least 100. So 100 would be somewhere above that. And we want to know which ones will travel at least, so more than 100 would be this area right here. All right, so we want to know what the proportion is or what the area is. That's going to be normal CDF. For the lower, that's going to be 100. For upper, pick something really big like 200. And then for mean and standard deviation, again, make sure you include those. The mean was 94, standard deviation was 2. So on the distributions menu, normal CDF, 100 for lower, 200 for our upper, oops. And then mean was 94, standard deviation is 2. And so it looks like very few, only 0.0013 of his fastballs will go at least 100. So not very many. For part B, what proportion of his fastballs will travel greater than 100? Well, at least 100 and greater than 100 you would think would be slightly different. This one is greater than or equal to 100. The next one is strictly greater than 100. It actually turns out, though, that they're the exact same. So whether you include 100 like we did in part A or don't include 100, the area is still equal to itself. So the answer for A and B is actually the exact same. So let's go ahead and move on to C, about what proportion of his fastballs will travel less than 90. So again, let's just kind of visualize what that's going to look like. Our mean is 94, less than 90, so 90 would be somewhere over here, and we want to know less than, so to the left of. So as we set up our normal CDF, for lower, pick something really small like 0. For upper, we'll have to use 90, and then for mean and standard deviation, we'll use 94 and 2. All right, so going back to our normal CDF option, and then for lower, we're going to use 0. Upper is 90. Mean and standard deviation, we're going to leave the same. And so that tells us that only about 0.0228, so a little bit over 2% of its fastballs will go less than 90. All right, for D, again, this is a nice one where it's giving you both of the intervals or both of the endpoints, so I wouldn't necessarily think you would need to draw a picture. Feel free to do one if you would like one, but we're going to go from 93 up to 95, and mean and standard deviation 94 and 2. So the nice part when they give you both intervals is you can kind of get away without drawing the picture and just using those as your lower and upper to get that about 38%, so 0.3829 would travel between 93 and 95. All right, for E, here's where we're going to have to switch gears a little bit. So what is the 30th percentile of Kershaw's distribution of fastball velocities? So 30th percentile, we don't know exactly what that value is, so I'm going to call that X. But we do know that the area to the left of X, which is our percentile, is 0.30. So because we already know the area, it wouldn't make sense to use normal CDF. Instead, we're going to use inverse norm to try to figure out what that value for X is. So we'll start by typing in area to the left, so 0.30, and then we'll use our mean and standard deviation, 94 and 2. So we'll again go into that menu, second vars. We'll choose option 3 for inverse norm. Our area is 0.3. Our mean is 94. And standard deviation is 2. And so that'll tell us that X is going to be equal to 92.95 miles per hour. So only about 30% of his fastballs will travel less than around 93 miles an hour. All right. And for F, what fastball velocities would be considered low outliers for Kershaw? So typically when we think about outliers, we've been using the 1.5 IQR rule. So remember 1.5 IQR is one way to find outliers. The other way, which is somewhat convenient, is plus and minus 3 standard deviations. Now in this case, we just want to know what would be considered low outliers. So if you start at your mean and then go down by 3 standard deviations, and each standard deviation is 2, then you end up with 94 minus 6 is 88 miles per hour. So basically anything less than 88 miles per hour would be considered a low outlier. And then high outliers, you could do something similar. You would just add by 3 standard deviations. That would be 94 plus 6 is 100. So anything more than 100 miles an hour would be considered a high outlier. All right, so in part G, we're going to do something similar to what we did in the previous example. So suppose now that we've got a different player's fastballs that has a mean of 92 miles per hour. So let's draw his normal distribution, 92 in the center, and 40% go less than 90. So you've got 90 somewhere over here. You know the area is 0.4. And then we want to know what is his standard deviation of fastball velocities, assuming the distribution can be modeled by a normal distribution. So remember before we didn't know the mean, this time we didn't know the standard deviation. The first thing we're going to want to do is find a z-score for 90. And we're going to do that using the 0.4 and inverse norm. So inverse norm, area to the left is 0.4. For the mean and standard deviation, even though we know the mean's 92, we don't know standard deviation. So we're going to just have to find the standardized or the normal score, the z-score, using 0 and 1. So we're going to go second, distribution, choose option 3 for inverse norm. Area to the left is 0.4. Our mean is going to be 0, and standard deviation is going to be 1. So our z-score is going to be negative 0.2533. And again, let's plug everything into our equation that we've used before. So x minus mu over sigma. And let's plug everything in. So z is negative 2.533, or negative 0.2533. Let me get that written correctly here. So 0.2533 is equal to x, which is 90, minus the mean, which is 92, over our standard deviation. Let's go ahead and simplify a little bit. So let's go ahead and rewrite 90 minus 92 is negative 2 over sigma. So now let's go ahead and multiply each side by sigma. So what that's going to look like as an equation is we've got negative 0.2533 multiplied by our standard deviation sigma is equal to, on the right side, negative 2. So to get sigma by itself, we're going to divide each side by that negative 2.533. And that should end up giving us our value for the standard deviation. So we're going to take negative 2 divided by the number that we got right here. And that ends up being about 7.89 miles per hour. All right, guys, that wraps up Unit 3 for us. So we will start to review and get ready for the test at this point. Until next time, have a great rest of your day.